Great. Okay. Well, welcome everybody to the first seminar of 2022 for the Monsoon Seminar Series. And so before we get started in introducing our speaker for today, just housekeeping rules as usual. Please make sure at the end of the talk to type your questions into the chat, and then we can either read them out or call on your name, and then you can ask it verbally or orally, if you will. And that's pretty much all the housekeeping we have. And then before I forget, if you do want to join the mailing list for the Monsoon Seminar Series, please go to our website or our announcement, and you can either email me or one of the other hosts to kind of join the mailing list. And you'll get videos and just announcements about everything going on here. And so without further ado, we have Dr. Prasanta Sanyal joining us today from the Indian Institute of Science Education and the Research in Calcutta. So you will be telling us a little bit about today, the Indian summer monsoon and the winter monsoon. And so again, I'll hand it over to you. Thank you very much.
Thank you, Tara, for the introduction. So a belated Happy New Year to all of you. And I hope that in 2020-22, we'll do better in terms of fighting with the COVID situation. So today, I'm going to discuss about the Indian summer monsoon precipitation and winter monsoon precipitation during Holocene. And these monsoon precipitation reconstruction we have done based on the isotopic composition of organic molecule. And I'll also try to discuss about the forcing factors in these two monsoon system. Now, if you see the way we use the monsoon word, it is almost, we have made it almost synonymous to the rainfall. But if you see the definition of monsoon, it is actually the seasonal reversal of winds. So what happens during the summer, the wind from the ocean goes to the continental part, this Indian subcontinent. So as the winds go from ocean to the continent, so it carries a lot of moisture and it causes rain in most part of Indian subcontinent. During winter, what happened? The winds actually blow from the continent to the ocean, and as the wind comes from the continent, so it is mostly dry, and that's the reason you don't get much rain or precipitation in Indian subcontinent. But if you follow the wind trajectory for this part, so you can see they are coming over the Bay of Bengal here. Now, as it comes over the Bay of Bengal, so it picks up moisture from here. And then while traveling through the southern part of India, it makes rainfall here, which is known as winter monsoon precipitation. Now, if you see the distribution of Indian summer monsoon and its trends, it's the following. So this figure, the figure A, it shows the distribution, variation, spatial distribution of Indian summer monsoon. So here you can, if you follow the scale here, so you can see the annual rainfall can vary from say 400 millimeter to as high as actually 4,000 millimeter. And if you see the trend for say last 60 years or so, so you can see that in northern central part of India, this blue color, and if you follow the scale, so it's actually negative. So that means in this part of Indian subcontinent, the Indian summer monsoon is decreasing, and the decreasing amount is around 15% of the total rainfall we receive here. Now, similarly, if you see the Indian winter monsoon, so here in this map, you can see the distribution, spatial distribution of northeast monsoon, that's the winter monsoon. So here you can see that the winter monsoon causes rainfall mostly in the southern part of India. And if you see the scale here, so the average rain will be around 600 to 700 millimeter in this part. And if you see the trend for last 59 years, so you see here, it's actually reddish in color. And if you follow the colors in the scale, so it's actually positive. So that means it suggests that the northeast monsoon, which causes rain in the southern part of India, it is increasing with time. Now, if I compare these two monsoonal trends, so that means the north central part of India, Indian summer monsoon, it is decreasing. And in the southern part of India, this northeast monsoon is actually increasing. Now, naturally, the question comes whether this inverse trend or the inverse relation between Indian summer monsoon and Indian winter monsoon, whether they are in envelope of natural climatic variables, or this inverse relation is the influence of the anthropogenic processes like or the impact of anthropogenic processes like warming up of the ocean. So in this talk, I'm going to discuss, or I'm going to show like when this inverse relation started. So these are from the instrumental records, but if you want to go back in time, you need to rely on proxies. So in today's talk, I'll be discussing how we have reconstructed this past rainfall variation for winter monsoon as well as for Indian summer monsoon. And we'll try to see whether this inverse relationship is the result of the natural climatic variables or it is the impact of anthropogenic processes. Now, how do you reconstruct rainfall? So if you want to go back in time and you want to reconstruct the rainfall variations, so you need sediments, and at the same time, you need to know the age of those sediments, and then only you can reconstruct the rainfall variation. Now, there are three different reservoirs one can consider for rainfall reconstruction, or for that matter, monsoon reconstruction. One, you can consider the marine sediments. Now, in most of the cases, in the ocean, it actually reflects the wind speed. You do not get the signature of the precipitation as such. Even if the rivers, which actually transport sediments or say organic matter into the ocean, and if you consider them, or if you want to consider them as a proxy for rainfall, what happens that you generally get averaged out monsoonal rainfall signature. The second reservoir is the river sediments. As river actually responses to the monsoonal precipitation variation, so in principle, the river should also document the change in the climatic pattern. But the problem with river sediment is that in most of the cases, the sediment records are actually erosional in nature. So it's very difficult to get continuous climatic record from river sediments. The third reservoir is the lake sediments. So the most of the cases, the lakes sedimentation in lakes are actually continuous, but it has also its own limitation. So in this talk, I'll be discussing how we have used lake sediments to reconstruct these two monsoonal rainfall variation. Now, as I said, that we have used isotopic composition of organic molecule to reconstruct this past rainfall variation. So let us see what are the different sources of organic carbon in lake. So in lake, what happens? So the organism who lives on the bottom of the lake, normally they take carbon from the dissolved bicarbonate. The organisms which are surviving on the surface of the lake, so they take carbon mostly from the atmospheric CO2. And in addition to that, with the surface runoff, the organic matter from the catchment area, they are also get deposited in the lake. So you have three different sources of organic matter, and the carbon isotope in this organic matter, they are characterized by distinctly different values. Now, to understand the climatic condition at the catchment areas, what you need to do, if you can separate out the signature of these catchment vegetation from these lake sediments, then you can use those organic matter to reconstruct the climatic variation in the catchment areas. So that is what we have done. So what we have done is we have first characterized the vegetation which were growing in and around the lake that is in the catchment areas. If you see the modern vegetation in terms of carbon isotopic composition, you can group them broadly into two different groups. One is C3 plant, the other one is C4 plants. So when we characterize the C3 plant in terms of their carbon isotopic composition, so we observe that the carbon isotopic value is around minus 29.6 per mil for C3 plants, and for C4 plants, the value is around minus 12.7. So here I would like to mention that this carbon isotopic composition of the C3 plant we observe here is actually 2 per mil more lower compared to the global average, which probably suggests that once you try to reconstruct past climate for a particular area, so it is important to consider the regional the regional character imbibed in the plants. So as you can see here, the C3 plant is 2 per mil lower compared to the global average. Now, problem with this bulk organic matter is that if you see these organic matter, the bulk organic matter, so they are consist of different compounds. So in this table, you can see the carbon isotopic character. So if I take this 0 as the carbon isotopic composition of bulk organic carbon, so you can see the carbon isotopic composition of this compound can deviate from this bulk value. So sometimes it can be lowered, the isotopic composition can be lowered, and sometimes it can be higher. So imagine that you are reconstructing vegetation from a place, and then you are observing the carbon isotopic variation in the organic matter. So that variation can be because of these preservation potential of these compounds, or it may be due to the variation in the abundance of C3 and C4 plants. So how do you tackle this situation? So here, what one can do, out of all these compounds, so lipid is considered one of the most stable compounds, and these lipids you mostly get in the as a waxy coating in the plant leaves. And these lipids are also consist of different compounds. One of the compound is alkane, and if the alkane is produced by plants, so they show distinct pattern in their carbon chain length and their distribution. Here you can see this is a alkane spectra from a sugarcane leaf. So here you can see the carbon number 29, 30, sorry, 31, 32, 33, 34, 35. So if you see the abundance of these odd carbon chain number like 29, 31, 33, and here 35, and here 37. So their abundance is higher compared to its neighboring even number carbon like 30, 32, 34, 36. So these patterns indicate the alkanes are derived from the plants. Now, once you know that, okay, the alkane are characterized like this in terms of their abundances, you also need to calculate the carbon isotopic composition of this chain for both C3 and C4 plants. And that is what we have done. So here in this plot, you can see in the horizontal axis, we have alkane carbon number like 27, 29, 31, 33, and 35. And the vertical axis is the carbon isotopic composition of these long chain alkanes. And these green vertical bars for the isotopic composition of the C4 plant, and the blue bar is for the isotopic composition of the C3 plant. So here also you can see, like bulk isotopic composition, the C3, C4 plants were characterized by distinct isotopic composition. So the same relation you can also see here. The carbon isotopic composition of alkane in C4 plants, their average value is around minus 20 per mil. And for the C3 plant, the average value is around minus 30 per mil. So as these two different alkanes is characterized by distinctly different isotopic composition, so one can actually use this isotopic composition to understand the vegetational pattern, or how the vegetations have evolved with time in a place. Now, once you know that the plants, as I showed, that the alkane pattern in the plant is like this, plant leaf is like this. Now, once the plant dies, and then the organic carbon or the organic matter from the plant get incorporated into soil, and then from the soil, it is actually transported into the lake. So you need to make sure that during this incorporation of the alkane into the soil and then finally into the lake, the pattern you observe in the leaf, the same pattern of the alkane is preserved in the sediment. So here, what I have done, I'm showing you one alkane spectra from the sediments. So you can see the similar signature, like the higher abundance of odd carbon, they're still preserved. So you can see 25, 27, 29, 31, 33. So you know that the character of the alkane has not changed. So these give you confidence to use their isotopic composition in paleoecological reconstruction. Now, it was about, so the last few slides I discussed about the carbon isotopic composition. So similarly, when plants grow, so they take the water from the soil, and the source of the water in the soil is actually the local rainfall. Now, in this alkane, the hydrogen isotopic composition is actually controlled by the hydrogen isotopic composition of the soil water, which finally determined by the hydrogen isotopic composition of the local rainfall. So what we have done, like we have done for carbon isotopic composition, we have also tried to understand the hydrogen isotopic composition variation in the plant alkane, and we have observed that the fractionation happen in different this lipid molecule, like in fatty acid or in the alkane. They are little different compared to the value observed elsewhere, which again suggests that for paleoclimatic reconstruction, regional consideration you have to take before you give a real, if you want to give a real picture of that area. These thing in background, that the isotopic composition of this alkane can be used to reconstruct past rainfall and past vegetation. So we selected 3 different locations. So one is a lake in Benital, which is in the northwestern Himalaya, and this lake is at an altitude of 2 kilometers. We have selected one section from the Banni Grassland in the western part of India, and one lake which is called Ennamangalam in the southern part of India. Now, the reason of selecting these 3 locations are following. So these 2 locations, like Benital and Banni, they receive rainfall mostly from Indian summer monsoon. But then why we have selected 2 stations? The reason is, see, Benital receives a very high amount of ISM rainfall. So it's the average rainfall is around 2,500 millimeter here. But if you see the rainfall in Banni, it is really very low. So here the annual rainfall is around, say, mostly 400 to 500 millimeter. And not only in terms of amount of rain, it is different. In terms of number of rainy days, that's also very low here if you compare the Benital area. And in the Ennamangalam, this area receives rainfall both from Indian summer monsoon as well as from the Indian winter monsoon. So these were the idea of selecting these three locations. So now let us go one by one and see what results we have obtained from these sites. This is the picture of Benital Lake, which is a relict lake. As I said, it is on the northwestern Himalaya and at an altitude of 2.5 kilometer. And if you see the modern vegetation in this area, so it is mostly dominated by grass and then shrubs and then trees. And 80% of the rainfall in this area we get mostly from Indian summer monsoon. The another reason of selecting this site was, if you see this boundary, this red boundary, is actually the boundary marks the dominance of ISM and the dominance of westerlies. So this area, the rainfall is dominated by westerlies, and this part is actually dominated by ISM. So our idea was, like, if the monsoon is affected, then this area will show it more because it is at the boundary of two different monsoon system. Now, as I said, that we have used organic matter from the lake to understand this past climate. What we have done, we have tried to understand the organic matter dynamics. That's how the sources of organic carbon varied in the lake. For that, we have used the C/N ratio. So if the C/N ratio is very high, it's more than 10, so then you can conclude that mostly the organic matter is derived from the terrestrial higher plants, that is the C3, C4 plant. If C/N ratio is low or it is less than 10, then in most of the cases, the source of organic carbon is the in situ, that is, the organic carbon was produced within the lake. So here you can see from the C/N ratio, even though there were fluctuations in the C/N ratio, but mostly it is suggesting that the dominant organic carbon fraction is actually from the catchment area. And that is what we need, because as I said, that if you want to reconstruct climate, this catchment plate, the catchment organic carbon is the best one to select. In addition to this, we have used other indices, which is known as ACL, that is average carbon chain length for the alkane, and also another indices called TAR, which actually suggests whether the organic carbon was derived from the catchment area or it was sourced within the lake. So this TAR index also suggests that the higher values also suggest that the organic carbon was transported from the catchment area. So this is about the sources of organic carbon in the lake. And then once we are sure that the organic carbon was dominated by the catchment area, then we measured the hydrogen isotopic composition in the alkane. So this graph you can see, so in the vertical axis we have age, which is in kiloyear, and the horizontal axis we have hydrogen isotopic composition of the alkane. Now, if you see the variation of this hydrogen isotopic composition from say around 10.5 kiloyear onwards, so at around 10 kiloyear, suddenly the hydrogen isotopic composition of the alkane, and the value got lowered, and the value is low, as low as around minus 270 per mil, and after that the value increased. And then, even though in this graph it is suggesting that it is more or less steady, but because the range of the value is such that, see, the trend normally we expect here, you cannot see here. So what we have done, we have the value after say 7 kiloyear or 8 kiloyear, we have plotted separately in this graph, where you can see that if you keep the axis from say minus 210 to minus 120, so it shows that the hydrogen isotopic composition of the alkane, it has got increased. Now, how do you explain this lower value and this higher value of the of the alkane. So for that, we have taken the help of the daily rainwater. So in this plot, the horizontal axis, we have rainfall amount. In the vertical axis, we have hydrogen isotopic composition of the rain. So here you can see if you increase the amount of rain, so the hydrogen isotopic composition gets lower, which is normally we consider as or termed as amount effect. Even though recent studies suggest that maybe the amount effect is not the only factor which control the isotopic composition of the rain, but broadly you can say from this data that it exerts some control on the isotopic composition of the rain. So based on this amount effect, what we have done, we have explained or interpret this lower hydrogen value is a phase where the monsoon was very high, and this higher value in the hydrogen isotopic composition we explain as a drying up period. Now, if you compare the hydrogen isotopic composition with the carbon isotopic composition of the same alkane, observe that the kind of lowering you observed in the hydrogen isotopic composition, you don't see similar kind of fluctuations in the carbon isotopic composition of the alkane. So of course, if you go to the higher part, you can see the carbon isotopic composition gradually got higher. So these probably suggest increase in the C4 plant in the catchment area. But the most interesting part, what we thought, is in this area where when you have had high rainfall, but the carbon isotopic composition is not reflecting that higher variation. What could be the reason? So to understand that, what we have done, we have grouped our data into 3 time zones. One is 10 to 9 kiloyear, the other one is 9 to 7 kiloyears, and the third one is 6 to 0.8 kiloyear. So what we have done in these plots, see the horizontal axis, we have plotted hydrogen isotopic composition of alkane, and in the vertical axis, we have plotted carbon isotopic composition of the alkane. Now, if you see the range of the value here, so it is say around minus 200 to minus 100. But if you see this graph, the value is around minus 300 to minus 150. And here from minus 160 to around minus 100. So you can see in the middle one, the range of value is very high. And as I suggested previously, that the value of hydrogen isotopic composition around minus 270, it suggests that the rainfall was very high. So that means even though data are very less here, but still it suggests that when you have very high rainfall, so if you see the correlation in these 3 plots, so here we have 0.72, 0.58, and 0.70. So correlation between the carbon isotopic composition and the hydrogen isotopic composition is actually lowest here. So this lowest correlation we are getting when the rainfall was maximum. So what we interpret from here, that if you have very high rainfall, maybe the carbon isotopic composition of the plant is less responsive if you have very high rainfall. And indeed, one of our paper where what we did, we compiled all the carbon isotopic composition of C3 plant, and we plotted the discrimination of carbon isotopic composition. That means the carbon isotopic composition of atmospheric CO2 and the difference between the carbon isotopic composition of atmospheric CO2 and carbon isotopic composition of the leaf. And in the horizontal axis, we have plotted the mean annual precipitation. So you can see that when in this lower zone of mean annual precipitation, the discrimination value is high. Now, once you cross the value around say 1600 millimeter, the discrimination value is flattens out. So the response is not that high. So it also supports our observation, the previous observation, that if you have very high rainfall in that kind of situation, maybe the carbon isotopic composition of plants is not a good proxy to understand the past rainfall variation. So then we went to the western part of India. So that's the Banni region. So Banni region is the Banni Grassland is one of the largest grassland in the Southeast Asia. If you see the rainfall pattern, so as I have mentioned previously, so this area also receives rainfall during the summer months. So you can see from the months here, and the average rainfall here is around, say, 300 to 400 millimeter. But I think the important issue is here the number of rainy days. So number of rainy days are really very less in Banni region. So again, here we have separated the alkane from the sediments and then measured carbon and hydrogen isotopic composition. So this graph here we have plotted the carbon isotopic composition of alkane C31, and also we have plotted C29. And in this graph, we have plotted the hydrogen isotopic composition for both C29 and 31. You see so in the vertical axis, if you see the age, so here we have age around, say, 5,000 years to the recent. The same is for the hydrogen isotopic composition. So if you see the pattern or the trend of change in carbon isotopic composition, so you can see it is a gradual hiring of value, so which probably suggests that with time the C4 plants have increased, and for the hydrogen isotopic composition, so if you see the value here, so the lowest value you see is around 100 minus 135, but as you go up, the values are really very high. Now, even though initially we explained these hiring up of the hydrogen isotopic composition due to decrease in Indian summer monsoon, but recently we published a paper in TCA where we showed that if this higher value in the alkane hydrogen isotopic composition can also be attained if the leaf experienced the burning. So what we have observed in the sediments that they are characterized by presence of charcoal, which probably indicate the presence of fire when these vegetation were growing. Here I'd like to mention that in most of the time during the vegetation reconstruction, we have mostly considered the climate is an important factor, at least for Indian subcontinent. But with the evidence of charcoal, maybe we need to rethink our climate theory, and I think we need to understand how the fire also played important role in shaping up this vegetation in the Indian subcontinent. So then, to explain the lowering of ISM in last 5,000 years, so we try to correlate with the forcing factor, and I think it's commonly used idea that the decrease in solar insolation actually led to the decrease in Indian summer monsoon in the late Holocene time. Now, while analyzing this monsoonal data from different sites, what we have observed, the relative change in the proxy value. What does that mean? Suppose if this is the data from the Benital lake, the Himalayan lake, and this is from the Banni Grassland. So if you see the spread in the isotopic composition here, so it is very high compared to the spread you see in the Western India. So what we observed that as you go away from the Himalaya, the relative change in the proxy value, it shows more or less decreased pattern. And here these green records, green column are for the continental records. And if you see this blue one, it's actually the marine record. So here you can see that in the ocean record, the signature of the variation in the relative change in the proxy is actually much lower, which probably again suggests that, so if you try to reconstruct from monsoon from the ocean, it's probably averaged out signature. So this is all about the Indian summer monsoon. So let us now go to the southern part of India. So in southern part of India, if you see the rainfall pattern, so here in the vertical axis, we have rainfall, and in the horizontal axis, all months. So you can see that the maximum rainfall is in the winter in the northern hemisphere, but you also receive rain during the summer months also. So what we did, we tried to understand the sources of the vapor in Chennai, one of the sites where we were collecting rainfall. So what we observed that during summer, the rain is coming, the moisture is coming from the Arabian Sea, and during winter, the most of the moisture is actually sourced from Bay of Bengal as well as the southeastern part of this Arabian Sea. So dominantly, it is the balance between the source Bay of Bengal and the Arabian Sea for the rainfall in Chennai. So when we try to understand the isotopic composition variation, so here you can see in the vertical axis the monthly precipitation. Here you can see the isotopic composition of the rainfall. So you can see that during the winter months, the rain happens, they are characterized by the lower isotopic composition, hydrogen isotopic composition. So one of the theories that this for this lowering in the hydrogen isotopic composition in the this northeast monsoon is that the source of the water moisture. So there are paper which suggested that the moisture is actually derived from the Western Pacific, and because of the long distance transport, the hydrogen you get in this area, they are depleted in heavier isotope. Now, this data is from the Chennai, which is a little away from our study site. So to understand whether these value can be used or for our study site or not, what we have done, we have used this online isotope precipitation calculator. And if you see this axis for our study site and the Chennai, so they are more or less similar. So with this logic, we have used a Chennai precipitation isotopic composition to understand our proxy record data. So here in this slide, in this graph, this plot is actually showing the hydrogen isotopic composition in the alkane, and this vertical axis is the time. So here you can see that from 5,000 years to around say 3,000 years, even though there is a small fluctuations, but you do not see any trend. But subsequent to 3,000 years, the hydrogen isotopic composition, it shows a gradual lowering. So this lowering in hydrogen isotopic composition, we have interpreted as the increase in the winter rainfall. So just for comparison, I have shown this plot, but just for comparison, you can see here, this is for the evolution of Indian summer monsoon. So here you can see that from 2,500 years onward, the isotopic composition, they show in the higher trend. So that means these two rainfall pattern, the winter monsoon and the summer monsoon, they are in actually antiphase. So when we compare the carbon isotopic composition of the alkanes, so here these data are from the southern part of India. So here you can see that subsequent to 3 kiloyear, the carbon isotopic composition, it is showing lowering in the value. So the lowering in carbon isotopic composition in the alkane suggests the increase in the C3 plant. But for the comparison, this graph I have put is again from the Banni Grassland. Here you can see that the carbon isotopic composition of the alkane, it is showing hiring up. So this hiring up of carbon isotopic composition suggests that the abundance of C4 plants has increased. So that means if you have two different climatic system, the response of vegetations are also different. So with winter rain, the C3 plants were favored, and with the decrease in the summer rainfall, C4 plants were favored. So this is also suggested by this correlation plot. Here you can see in the Banni, so this vertical axis for the carbon isotope and the horizontal axis for the hydrogen isotopic composition. So here you can see that they are showing good correlation, and the same is true for the southern Indian data. So the vertical axis for carbon isotope, the horizontal axis for the hydrogen isotope. and it shows a good correlation which suggests that the winter rainfall actually favored the abundance of higher abundance of C3 plants. Now, you also try to see the correlation of this Indian northeast monsoon and the Indian summer monsoon with the other monsoonal system in the world. In this graph, you can see that this line is for the Indian summer monsoon, and this blue one is for the northeast monsoon, that's the winter monsoon. And this data is from the Dongi Caves. It is actually East Asian summer monsoon. And this data is for the Australian, Indonesian summer monsoon. So if you compare this Australian, Indonesian summer monsoon data, it shows a similar trend with that of the Indian winter monsoon. Now, as I said, that for the modern precipitation record, so what people have suggested that for this northeast monsoon, the ENSO play a more important role compared to other regional oceanic phenomena. Like, for example, if I consider Indian Ocean Dipole, so the correlation of Indian Ocean Dipole Index with the northeast monsoon is actually lower compared to the ENSO. Here you can see that at 3,000 years onward, the ENSO events per year, it shows increase. So that means that ENSO probably played a major role in controlling the winter precipitation in the past also. Now let us see that how this ENSO can impact the source or the northeast monsoon or the winter monsoon precipitation. Now, what you need to do for that, all you need to do, you need to explain how the ENSO has impacted the generation of moisture in the Bay of Bengal and how it was transported to the southern part of India. Now, to understand that, what we have done, we have considered the ocean temperature, and towards that we have used two different indices. One is the tropical cyclone heat potential, because as you know, for the monsoonal rainfall, the cyclone which actually brings the rain in the land. So we have calculated the tropical cyclone heat potential in the Bay of Bengal for a designated area. And we have also calculated the mixed layer heat content. So when I say mixed layer, it means is the depth at which the potential density is 0.0125 kg per meter cube more than the surface. If you see this mixed layer heat content, so here you can see in this figure, this box we have considered as the source of the moisture. So here you can see, and if you see follow the scale here, so the mixed layer heat content is high here. And if you see the trend of mixed layer heat content for last 55 years, you can see the scale here. This white is in color, so this white color indicate that it's increasing. So that means the increase in mixed layer heat content suggests the higher evaporation in the source area. Now, when we consider the cyclone heat potential, here also you can see it's very high in the source region. And if you see the trend for last 59 years, you see from the scale here, it is also increasing. This increase in heat potential suggests that the higher number of cyclone generation in this area, which probably contributed or resulted in the rain in the southern part of India. We also try to see how the moisture flux has varied with time. So here you can see the difference in moisture flux between the El-Nino year and the normal years. If you concentrate on this part of the Bay of Bengal, you can see the values are actually positive. So it suggests the moisture flux divergence from this area. And if you concentrate or focus more on the Indian side, rather than comparing the global pattern, here also you can see the values are positive. So that means it provided moisture for the precipitation in southern part of India. We also try to calculate the pressure difference between the El-Nino years and the normal years. And from the scale here, you can see that in the Bay of Bengal, the pressure is positive, and here it is less. So that means when the moisture is getting generated here, they will be transported from this direction to this direction, and while doing so you get precipitation in the southern part of India. Now, when I say that we compared this northeast monsoon with the cyclone heat potential and the mixed layer heat content, even though from these graphs, so this graph is actually correlation comparison between the rainfall pattern from the northeast monsoon and the variation in the TCHP. So, and this graph is actually for the variation of northeast monsoon and the variation in MLHC. So you can see between these two graphs, even though they show correlation, but you can see the correlation is better for mixed layer heat content compared to the TCHP. We also calculated the oceanic potential temperature for last 3,000 years from the trace 21K data, which also suggests that the oceanic potential in the temperature in the Bay of Bengal, it has increased with time, and which is also reflected in the Arabian Sea expansion of the Arabian Sea warm pool. So here you can see that at 5,000 years, if you see the width of this Arabian Sea warm pool, and at 3,000 years and at 1,000 years, the width of the warm pool, you will realize that from 3,000 onward, the width of this Arabian Sea warm pool has increased. Now, with this analysis, if I come back to this question that whether the modern trend of inverse relation between the northeast monsoon and the southwest monsoon, whether they are anthropogenically influenced or they come within the envelope of natural climatic variables. So from the analysis which I showed, which probably suggests that at 3,000 years, you don't expect the anthropogenic forces. So that means even though probably we cannot ignore the recent impact of recent warming in the monsoonal system, but I think the ocean was enough warm to cause this anti-phase relation between summer monsoon and the winter monsoon, and which is actually was within the natural envelope of envelope of natural climatic variables. So with this, I would like to summarize here. So as most of you know that the Indian summer monsoon has decreased in the late Holocene, but for the first time, at least I have not seen any climatic record which showed the past reconstruction of Indian winter monsoon. So our study suggests that the winter monsoon has increased in the late Holocene, and in comparison with the precipitation timing, what we observed that winter precipitation favored the growth of C3 plant, and again to this inverse relation between ISM and NEM probably falls under the envelope of natural climatic factors. And all these data I have presented here, these are all generated by my amazing students from whom every day I learn new thing. Even some of the modeling part I showed is done by one BSMS student. And if you want to know more about our work, you can follow our website. Thank you.
Great, thank you so much, Prasanta. Let's give everybody a moment to type in some questions. I see that we've had some comments during the talk, but before we get to that, I just wanted to ask a couple quick questions myself. So as another lake lover in the monsoon community, you might have briefly touched on this, but could you tell me a little bit more about how you establish the chronology in some of your systems? I think radiocarbon, at least for Banni and NE Monsoon, but I missed Benital, I think.
Yeah, so Benital was also by radiocarbon date, 14C.
Okay. And just, do you know the type of material that was analyzed? Was it just the
It's bulk organic matter.
Okay. Okay. All right. Yeah, I wasn't sure if you were using pieces of that or pieces of charcoal, especially in I think your Banni section. And then as my second short follow-up question, and I think you also touched on this, is with you mentioned there's an increase in charcoal in your Banni section. And you mentioned that this is probably more likely involved with people, with burning by people. Is that what I caught, or am I misunderstanding?
Yeah, I did not say whether the burning was by people or not. All I tried to convey is that if you have burning or if you have wildfire, they can actually modify the hydrogen isotopic composition of the alkane, and the enriched value, the high enriched value we have observed in the Banni probably suggests that it is the impact of the burning, whether it was by the people or it was natural wildfire. I really do not know.
Okay, well, in either case, they're both extremely interesting, I think. That would be kind of I think a cool avenue to explore, I think personally anyway, but I like ties between archaeology and geology a lot. So let's get on to, I think, some of the comments here, and please, everyone, make sure to type in some of your questions here for Prasanta as we go through some of these. Sanyal had a couple of comments. Did you want to elaborate at all, Sanyal, or ask any more questions?
Should I read the question? So resolution of the data set seems very poor for the mid to late Holocene. The number of data set in the 3 different population is less than 10 points, so better refrain from using correlation using this condition. Yeah, so this I think you are trying to mention about the 3 data segment we have. I have showed for the Benital one. Yes, for the middle one, the data is less. But as I said, that even with the higher number of data set, we confirm that if there is high rainfall, and in high rainfall condition, the response of carbon isotopic composition in C3 plant is less. So that's the point I wanted to convey. And I agree with you that in that middle layer, like I think 9 to 7 kilo year, the data less. But in another paper where we have made a global compilation where we showed that if with the enough number of data set, that if there is high rainfall, the delta 13C value of the plant is less responsive.
Okay. Oh, here we go. We've got a couple of new questions here. We have one from Pramit. Did you want to ask your question out loud, or should I read it out for you?
Yes, thanks, Tara. I can read it out loud. Okay. So actually, first of all, let me tell you that I don't have any paleoclimatic background. I am just an ecologist. I work on the carbon and water cycle of terrestrial ecosystems. But it was a very nice talk to hear Professor Sanyal. So I have seen, and we have observed that the C4 plants have better water use efficiency than the C3 plants. I mean, they consume less water to sequester same amount of carbon as compared to the C3 plants. So my question is, can you give any insight whether that has been the same in the paleo scale as well? I mean, in the previous times also in the history of Earth, whether the C4 plants always have been more water use efficient than the C3 plants?
So yes, you are right that C4 plant is more water efficient. But I think the point which I try to emphasize here is the timing of rainfall. So if you have, say, winter rain, so that winter rain will favor more C3 plant rather than the C4 plant. But in terms of water use efficiency in the past, I have not done any work on that, but all the interpretation is based on the correlation between the, say, water isotope and the isotope which is related to the vegetation. So I don't think it is appropriate to say about the water use efficiency from that correlation. But I'm sure that in the past also it was probably like that. But I think the most important part is the timing of the rainfall. Whether the rainfall you are getting in the summer or in the winter, that's more important.
Yeah, that's very intriguing actually. I mean, if I'm allowed to carry a bit forward regarding this discussion. So most of the C3 plants, those are deciduous. And winter monsoon, those are favoring C3 plants. That is quite interesting topic because C4 plants are, more or less, they are coniferous, they are evergreens. So,
No,
but you
C4
are saying,
plants are, sorry if I can interrupt you, C4
yes,
plants are
please.
mostly the grasses. It's mostly the grasses. So if I can use a colloquial term, like if you see the chore cutter, I don't know what you call it in English. So if you see this chore cutter, they grow only when there is summer rainfall, and they are actually C4 plants.
Okay. Thank you.
We have another question from Sarthak. Would you like to ask your question, or Sarthak?
For Sarthak, it is well known. So it's most of the plot I showed, it is actually done by Sarthak only. So I don't know what question he has. So it is well known that the northeast region does not show amount effect. The authors have not used the amount effect in this region, but that of Delhi is justified. So yeah, I can understand this question. So because we do not have much data from Chennai, so we cannot really talk about the amount effect. All I try to interpret is that based on the data we observed from the Delhi, and I can understand that there can be a reservation on that, but that's the best thing I can do at the moment.
Okay, great, thank you. Does anybody else have any more questions for our speaker today? I'll give you a moment to type them madly into the chat.
So who is this Sunil BSIP? I think he's kind of abusing, so I really don't know what he wants.
I think he just had or they had more comments about the talk. I'm not sure if Sunil is still even here in the audience.
Okay.
Yeah. Okay. So I had maybe one more. We have one.
So Habibullah, so you can.
Yeah, Habib.
It's for reconstruction to ask. That is there.
Yeah, it seems like we've missed part of his question. Habib, are you able to ask your question or type more of your question? I think we've missed part of it. Well, maybe while we give, and then we have another question from Ankit.
Ankit, do you observe any trend in Sri Lanka precipitation? So I have not gone through the paper. I heard that recently they have published one paper which actually showed the increase in precipitation during winter. But I have not seen that paper thoroughly, but I know there is a recently published paper.
Great. Well, I see that it's 8, or well, at least it's been an hour of your time in presenting your presentation and your research from yourself and all of your students and colleagues in your lab, and we appreciate that.
Thank you.
Habib managed to write in part of his question.
How many points are required for reconstruction?
I think it's more of asking how many that you need, like a minimum. I think that's what maybe they're asking.
Yeah, I think the more data you have, it's better. But many times, in terms of number of sample, we do face restriction. But yeah, but the answer is the more data you have, it is good for your analysis.
Yes, very solid answer there. More data. Okay, well, I think that we'll hold the questions for now, and again, put our hands together for our speaker, Dr. Prasanta Sanyal today. And so before all of you run away, please remember, if you want to join the mailing list to get announcements for new speakers and things like that, just shoot us an email. And then make sure to attend next week if you can, or catch some of the recordings either on YouTube or that we distribute on the mailing list for Sergio Ondo. on the 26th of January. So again, thank you very much to Dr. Prasanta, and I will put my hands together.
Thank you. Thank you.
Thank you.